Yeah, good morning. Let us resume our discussion. So what were we discussing in the last class? Can any of you brief quickly?
We were discussing about filtering and the design of filters, filters related to constant regions, edges, corner points.
Okay, we were discussing about filtering. How filters help us extract features. How they help to enhance the constant or uniform regions, or to extract some features like edges, or corner points and so on. Correct? So we have actually discussed about feature extraction through filtering. Okay, or convolution operation or correlation operation. That's what we have discussed in the previous classes. Okay, so now let's resume our discussion, or let's continue our discussion further on the feature extraction. So just to have a clear idea and to reinforce the importance of feature extraction, why do we need the feature extraction? Can one of you tell? Any quick inputs on why do we need feature extraction?
So that we get efficient features for ML classification task.
Okay, for any classification task. Okay, what else? Any other or any other task that where we need the feature extraction?
Identification, recognition.
Detection.
Okay, identification and recognition. Of what? Of any object, face, and so on. Okay, where else? What are the other computer vision tasks? Can you name some of the computer vision tasks other than what we have written here?
Image detection. Segmentation.
Object detection. So object detection means what? What do we do? So in a given image, okay, we want to identify a particular object. So let it be car or whatever. We want to identify a particular object. Okay. So this is object detection. So we put a bounding box around the object. That is referred to as object detection or localizing the object. Okay. Okay. What are the other computer vision tasks other than object detection?
Tracking. Object.
Tracking, visual tracking. They call visual tracking because they are tracking based on images or sequence of images. Okay, so you have actually a image here. You have a next image here. Okay, and then you want to track. Say if there is a car here. Okay, where is it? In the next frame. Okay, if there is a person here. Okay, if where is the person in the next frame. Okay, we want to track it. So from here to here, what's the like the motion? So from here to here. Previously center was here. Okay, from here to here. Okay. What is the other computer? Segmentation. Okay, segmentation. Here we want to segment a particular object. So exactly we want to give a boundary for the object. Okay, say for example, if there is a red blood cell like this, or white blood cell like this. Okay, and then we exactly want to say that this is the white blood cell. Okay, and then a red blood cell is like this. Okay, we want to say exactly this is the red blood cell. Okay, and so on. So if there is a some other any aspect we would like to segment. Okay, it's in microscopic images, platelets, for example. Okay, we just want to say that there is a platelet here. Okay. So in street videos, for example, where cityscape videos, where you have actually person like road, okay, and then trees, okay, and so on. You want to exactly segment where it is, and then green again here, vegetation, okay, or whatever we want to exactly separate. This is a road. We want to. This is segmentation, okay, and then what is the other task? Any other task? Depth estimation. So what do we want to do in depth estimation? There also you have actually two images. Okay, you have two images. And then this is the left image and this is the right image, stereo images. And then what we want to do, we want to see a scene point, for example, or whatever, there is some tower here. From left to right image, there is a shift for this. Okay, so what we want to do is exactly where is this point and this point. What is the relative shift? Okay, this is the relative shift is called disparity, we call. Okay, small d. And then depth is equal to inversely proportional to disparity. Some say if there are two cameras are separated by baseline b, okay, and then their focal length is f, then bf by d. This is in essence actually depth is inversely proportional to shift, relative shift or disparity. Okay, we will see that little more elegantly or mathematically later, but these are the different computer vision tasks. So roughly these are the computer vision tasks. So any other computer vision task you want to name? Okay. So given that these are the computer vision tasks, in all of these things, what is common? What is important? Can you name some of the common aspects in all these computer vision tasks? Require what? All of these require what? See, for example, if I want to localize an object, I need to first identify some features of the object, right? If I want to track an object, don't I need to have the features of the object? If I want to segment a particular region with respect to the other region, don't we need to identify the features, and based on features we need to separate? And similarly, if I want to identify a corresponding point, okay, that means for this, where is the matching point here? Okay, so should I don't need the features around that point? Yes or no? So all these tasks require what? All the tasks require feature extraction. Is it clear or not? So this requires feature extraction. Other than feature extraction, what are the other things that these tasks require? Can you figure out any other things that all these commonly require? All these computer vision tasks. Any other very important aspect that, and it is common to all of them. Say if I have a template of car, okay, if I want to identify where it is, do I need to do matching or not template matching? Or should I not need to do correspondence between different points of car in the template and different points of car in the image or not? Similarly, if I wish to do tracking, even here, if I have actually some key points of the car, okay, should I not need to identify where those key points are in this both images? In this image, I have identified somehow car here. Okay, in frame 1, and this is frame 2. Frame 1 to frame 2, I need to identify where that point is. Similarly, where the second point is from frame 1 to frame 2. So I need to have the same template, the whole template identifying from frame 1 to frame 2, or I need to identify some corresponding points. Establishing correspondence between different pixels of an object in one image to other image is important in both detection and as well as in tracking. Is it not important in stereo based depth estimation? So I am say if I want to find out for each point, which is a corresponding point, should I not need to find which is the corresponding point, or which is the template of this object, where is it in the next image. So that each point I know how much disparity or the shift, relative shift does it has. Yes or no?
Yes, sir.
Yes. So we need to identify in each of these things, even if I want to segment, if I know the objects of interest, say if I know this is the, say this is how the white blood cells look like, or if I know this is how the red blood cells look like. Okay, so I try to find out similar characteristics in this image. So this matching happens here, not at the a particular template level, but at the feature level. Okay, in terms of segmentation also, we are finding the correspondence between the features of the class, samples of that class, versus where these kind of features are there in that image. So what is the other important task that is common for all these computer vision tasks, or other important subtask that is required for all these computer vision tasks? What is the other thing that is important for all these tasks to accomplish?
Template matching.
What's that?
Template matching.
Template matching. Some cases what we do is template matching as it is not easy. The reason being, see, this may be of different scale, and this may be of different scale. This car may be of different scale. This car may be of different scale altogether. See, this may be of different view. A person itself, when we want to match a person's face, for example, he may be of completely different view in other image. So the 3D objects may be of different views, different scales, different appearances geometrically and photometrically. The imaging also may be different from imaging conditions may be different, and the background and the background aspects also will be different. So photometrically, there may be variations on the images from one image or one scenario to other scenario. Similarly, from viewpoint and from scale point, geometrically also there can be variations. So now, given these variations, what is the other way of doing template matching? Say, assume that we don't want to completely match the template, but still we would like to make the correspondence happen. Okay, then in such case, how do we make this correspondence happen? Any idea on that? Other than template matching. Okay, what is, if you would like to write this as a common important task, subtask that is required in all this, we can write that as establishing correspondence, finding corresponding points. I hope you understand what is meant by corresponding points. Yes or no? So what is the difference between template matching and then finding corresponding points? Can one of you tell, just for the confirmation? What is the difference between template matching and finding corresponding points? Yeah, what do you think is the difference between them?
In template matching, we match each and every point, but in finding corresponding points, we just have to focus on some particular points.
Very good.
Like region of interest.
Correct. Very good. So the whole computer vision methods have evolved in these two different directions. The methods where we perform whole template matching is referred to as dense approaches. In some sense, what we do is I try to find in some sense either template matching, or for every point we want to find out the corresponding point. Okay, for every point we want to establish correspondence. Okay, correspondence is established for every point here. Okay, whereas in this kind of methods, which is referred to as feature-based methods, dense approaches we mentioned, right? So these are referred to as sparse approaches. sparse methods or feature-based methods? In this, what we do is we identify initially itself some of the very key points. So this will have two subtasks. One is identifying key points, okay, and then only establishing correspondence or whatever at the key points. So feature matching at key points. Okay, and hence we have also the results for results only at key points in some cases. In some other cases, we use these key feature or the results at key points and establish the results for the whole image, okay, or the whole region of the image, region of interest. That we take the initially sparse results and go to the dense results. Okay, so now if you would like to identify some of the key points or the feature points where we regions of interest points where we essentially want to focus or initially start with, which are the points do you suggest? So assume that in these different scenarios I have mentioned, I would like to take up this approach. Assume that I first want to find out key points where I should look the information for. Okay, so then what are the points do you suggest? The question is where to look. Or which are key points? Good key points. Okay, if you would like to approach this. Anyway, for this, we know how to perform template matching, extracting features and performing template matching. Here, the first task, as we said, is which are the key points. Okay, it's the same question is posed differently as where to look for information. Okay, and there, what information to look is again extracting features, feature extraction only. So that we are anyway discussing, and we will discuss further as well. Okay, so now this class discussion is mainly concentrated on where to look for information or how to find the key points, good key points. Yeah, any answer for this or any thought for this? So in a given image, say I have shown a car here, a person here, okay, and then a pyramidal structure here. Okay, in these different scenarios, where should I look? Which are the points which will help me to identify the information better? Some answer is expected. Yeah, where should I look? Say, for example, if I have a, say, I want to detect a car, which are the regions I should initially look for information? No idea on that? Say, to make
look at the two ends of the cars. You can use those
two ends of the cars. So we can easily say that actually so these are the two regions probably we can initially focus. Okay, fine. So if I give you pyramidal shape like this, and again here also I want to look for some regions where I initially wish to focus, are the interest points I would like to locate in this image. Which are the interest points in this image now? Which are the interest points in this image?
the tip of the pyramid.
Yeah. Okay, where else? This is one region. Where else?
Corners.
Corners. Very good. So now if we see all these aspects, which are very potential points, okay, are the key points to look at for information, easily distinguishable or high information, are the corner points. Now, what is speciality about these corner points? The question is why corner points?
Its intensity will be higher than its neighboring
Yeah,
pixels.
can you repeat,
So
Aditi?
the intensity will be more than its neighboring pixel.
We can see more.
The intensity will be more of
Okay.
the corner point than its neighboring points.
Okay, fine. So the scenarios may be different. See, for example, in this example, assume that inside all is say black and outside is white. So corner point may have a lesser intensity than the surrounding regions. Is it not?
The gradient of intensity.
Okay, very good. Gradient of intensity is high. Good. So the gradient of intensity is high, not only at corner points, but also at edge points. Is it not? Yeah, along the whole edge, I will have a better like gradient. Is it not? Then why corner points? Assume that I have an image. Just simply I have some something like this. Okay, and then probably okay. So and then like this. Oh, now if you see along the edge also, I have actually good gradient. Why are we looking for a corner points? Why not this point versus this point? So point 1 and point 2, which is more informative or which is easy to catch. Okay, for my matching or for my, okay, for matching, let it be at the point level. Okay, rather than at the template level. Matching, feature extraction, also uniquely matching. Okay, correspondence, all those things. Which point should I consider, P1 or P2? Both has high gradients. Uniform regions, of course, it may be dark and this region. Okay, that we ruled out just now. Okay, yeah. So which point, P1 and P2? P1, very good. So why P1 is the question now?
Because along P2 along the edge there will be zero intensity change, whereas corner gives high intensity change in all directions.
Okay, very good. So if you see if I want to match this point P2, P2 can be matched like it cannot be matched uniquely. It can be matched with any of these other points as well. Is it not? If you see actually between two templates, so this edge point, if I see, for example, let us bring this itself here itself. Okay, so this edge point, if I see, this edge point can be matched with respect to this point, okay, or this point, and so on. So if this is P3 or P0, okay, P0 can be easily matched with P2, P4, P5, and so on, P6. So all the points along the edge point match to another edge point. Is it not? So I can't make unique match. P0 is a match. Okay. For P5, P6, and I can make many more combinations. Okay. So the reason is corner point Y is because it can be uniquely matched. Okay, this is one important property. The other very important property that just now Abhimanyu has pointed out is what? The variance, okay, the variation in all directions with respect to the corner point is high. Variation of intensities anyway, or features, is high. Okay, that qualifies a corner point, and that is a very good feature for establishing a match. Why is it a good feature? Because that will help me to uniquely match between across images or within the image to the template and so on in all these computer vision tasks. So assume that now what we have seen is the points where you have actually variation of intensity in all directions are important points or interest points. They can be uniquely matched across different images, or they can be uniquely matched with respect to the template. So now the question is, how do we mathematically identify them? The reason being, see, image is a, say, sometimes it's a very big, okay, 1024 cross 1024 or 256 cross 256, and number of images are also very vast. See, if we take a video, 30 frames per second we are getting, and then we have actually each image is 256 cross 256. If I want to identify a person, where is it in the whole video? I just want to identify a particular person where he is in the whole video. It's not an easy job. And on the top of it, what we want to do? We want to see interaction between the persons and objects, persons and persons. And we want to know where two persons are together, where a particular person is doing what. Okay, action recognition, for example. And we also want to identify a particular object and its path, okay, or its track over the video. So these are all the different challenges that computer vision faces. So given all these challenges, it's not very easy to identify or perform these tasks on a large scale, unless we have a simpler method or a mathematically tractable method for identifying the points of interest or the regions of interest in an image. Okay, so now the question is, say assume that there may be several objects. Okay, there can be some car, okay, as we are thinking, and there can be some person, okay, and there can be some other building, okay, and many other things. So now the question is, in the whole image, I want to know where objects are, okay, where there is an important information to look for. Okay, so how do I do that? I need a mathematically viable method to capture the corner points. Assume that since we discussed so far and boiled down that the interest points are nothing but the corner points, are the points where they have high variance in intensity in all directions. Okay, so now I need to have a mathematical approach to figure out such corner points. How do we do that? What should be the mathematical approach for that? Any suggestion on this? What's a good way to identify corner points?
So change of slope.
Change of slope, fine. So I can find out, first of all, one suggestion is, if this is I of x comma y, assume that I have found ix, where ix is defined as dou by dou I of x comma y by dou x. Okay, so gradient in x direction. Okay, and also I have found iy, dou by dou x, I of x comma y in y direction. Okay, fine, good. Then what is the next step? I have found gradients in x and y directions. Of course, I can also find, if we write, so gradient g, okay, root of ix square plus iy square here. Okay, fine. Then what is the next step then? Any other suggestion? See, not necessarily you need to follow this. Okay, you can come up with your own method. That's how the field has been evolving. Any other thought? Say, assume that I want to identify this as a corner point. Okay, this is very clear corner point, right? So I want to identify this as a corner point. What is the suggestion you have?
We can find the difference in intensities in all the four directions, like we did earlier, like x plus 1 comma y, x minus 1 y. Like
Very
that.
good.
And if it's greater than some threshold, we can identify it as a corner.
Very good. So the suggestion here is, I calculate ix comma y minus I of x plus u comma y plus v. Okay. This difference for all u comma v. For all u comma v means u comma v belongs to minus 1 comma 1. That means minus 1, 0, 1. Okay. So if we, it belongs to minus 1 comma 1. You can also compute in the, say what the suggestion is, you take a template here Okay, you see how much the difference is with respect to this shift. Okay, this shift. Okay, this shift. Okay, and then this shift. Okay, and then this shift. All these shifts. Okay, so each shift you take, and with each shift, how much is the variation we want to see? That difference is now u comma v. Okay, I'm just writing difference in terms of d u comma v. I will see in all directions. Okay, and then I will see actually whichever shift has the, then I will see that what is the next step you said? I have to take the difference, and then
we have to, like, if the difference is greater than some threshold, we'll
okay,
quantify
greater
it
than
as a
threshold in any u comma v or for all u comma v. It has to be greater than threshold for all u comma. Okay, then only we say that in all directions, the gradient is high or the variation of intensities is high. Okay, so somebody is conveying that you can take the Gaussian distribution based 2D filter matrix. Fine, you better to convey in the class rather than messaging, unless there is a problem for the internet. See, you can take a Gaussian and so on, fine, but you should have a clear idea on how exactly we go. Okay, so for you, it looks like the intensity at the middle is a peak. Okay, but not necessarily it's always a peak. It need to be distinguishable from the neighborhood. So it means that, so it is actually, it can be a peak in positive direction or in negative direction. Further, it is also, say, as we have discussed in the previous classes, so the variation in all directions will be better captured not by Gaussian, but by Laplacian of Gaussian. Okay, that means in the middle, if there is a peak, and then it is the other sides, it is less. Okay, that shows a very clear idea. Okay, in 2D also, it's 2D Laplacian of Gaussian. This is second derivative of dou square by dou x square of g of x. Okay, drawn in with respect to x. Okay, this is Laplacian of x. Okay, so this is also helpful. However, actually you have to use this appropriately at all directions and then convolve with this and find. In fact, there is a very good method which provides the feature points or interest points based on this that we will discuss subsequently. Good, this is also a good method of doing. For easy to understand and initially to start with, this is a basic approach that we can easily understand and follow. So what we do is we see the difference in all directions, and then the difference of intensity in all directions is high. We can assume that it is a interest point or a key point. Now the next question comes. See, this operation I have to do at all points, and do we see the difference only with respect to the pixel or with a patch? The question is, see, if I want to take a patch around this point and find the difference, or I just take I of x comma y. Or the question is, instead of taking I of x comma y, should I take summation over neighborhood of x comma y? X comma y now belongs to neighborhood of x comma y. Neighborhood of x comma y means what? It's a patch. Okay. For all this, what I take is I of x comma y minus I of x plus u comma y plus u. You understand the difference between this and that? So I am just putting actually square here because the difference, whichever positive to negative, negative to positive, both are important for me. Okay. So the question is, should I take this or should I take this? Here I am taking a patch difference around x comma y, and here pixel difference at x comma y. Which is better?
patch difference is better.
Patch
Because
difference.
it will give broader perspective.
Yeah, it gives the whole information. Okay, information is there in a patch rather than a pixel. Pixel can also be noisy pixel sometimes. So patch usually avoids such difficulties. So this is what we do. And this has to be greater than a threshold. Okay, for all x u comma v. Okay, the here important aspect is if say for example, at the edge, what may happen? The difference will be very high in one direction. Okay, and the difference will be 0 in other direction. So in that case, what happens? It's not a corner point. It's not a very interest point. Okay, if we want to mark it as interest point, it needs that the variation in all directions is high. Intensity variation in all directions is high. Okay. Now the question is, how do we do this? The initial method that has found out interest points has come with this explicitly with this computation. Compute it at each pixel, okay, and see if this is greater than threshold at a given pixel. And if it is greater than threshold, you say that in all directions, you have to count out, do it for 9 times. Okay, even if you consider a small neighborhood, right? Even if you consider a small neighborhood of 3 cross 3, okay, you need to do for 8 times to compare. Okay, and then identify which is an interest point. And you have to do on 102 cross 1024 means how many times you have to do? 1024 whole square into 9. Okay, these many times you have to find for finding interest points. Okay, is it not? So these many computations, is it viable? It's not. So this is the method initially which does this or which suggested or proposed this is given by Moravec. And hence this operator which finds out this, so this difference at each u comma v and then compares with the threshold, okay, to say an interest point is referred to as Moravec operator. Okay. The later method, which is much more elegant and has been very widely used and overcomes many of the limitations of this, is being proposed by Harris. What the suggestion here is, can we simplify this? We don't want to compromise anything. Okay, so I want to find out the same objects wherever they are. Okay, and then the corners and so on. Okay, I want to find them. But however, can I simplify this? Can I identify them better? Okay, now the question is, how do we simplify this process of finding? Any idea on that? So the final expression we want to get is I of x comma y minus I of x plus. Hope what I'm writing you are able to understand. X plus u comma y plus u whole square. X comma y belongs to what? X comma y belongs to neighborhood of x comma y. Okay, neighborhood of x comma y means it can be 3 cross 3, 5 cross 5 and so on. So this summation will ensure that we are taking a patch. This essentially is for, okay, a patch difference. Okay, this is just doing patch difference. And where we are doing this operator now, if I write E of u comma v, it's finding at each u comma v. But see, u comma v is also for all u comma v, I will find. This is a function of u comma v fine, but at each x comma y also I am doing this. Please note that at each x comma y I am doing, but it is a function of u comma v. Okay, so for all u comma v I am doing, right? For all u comma v belongs to -1, 0, 1. Okay, and then x comma y belongs to what?
Neighborhood of x.
Yeah, all image pixels. Image grid. Okay, for all pixels. Fine. So now the question is, can we make this better through some of the mathematics or the concepts in mathematics? Can we simplify this? Can we pose it as an optimization problem? Or can we pose it as a much more elegant way of simplification rather than exhaustively looking for all u comma v? the main question has arisen. See, if we are looking for u comma v, different u comma v, what we are doing is we are checking here, we are checking here, we are checking here, and so on. So we can, even in a discrete git, you can check only for 8 combinations. But there can be other directions, okay, wherein u comma, the variance with respect to that object is, variation is less. Okay, so I would like to capture all continuum of u comma v without discretizing. U comma v, can we solve this? Have solution for this. If you would like to solve for all u comma v, this measure e has to be what? So okay, how should I pose the optimization problem as? That's the next question. What is the optimization I would like to achieve? Any suggestion on that? This u comma v only I'm writing because anyway we need to do it all x comma y. Okay, and hence u comma v is only the function I would like to highlight, because with respect to the all u comma v, we would like to consider, okay, some optimization. What should I do with respect to all u comma v? Any suggestion on this? If I define this as e of u comma v, okay, what is that I would like to identify? When which x comma y is a corner point or interest point? If what? Yeah. If, what is the condition now? Any suggestion on this? EU comma V, right, has to be what? So as we discussed before, what is the condition on this? Has to be greater than or equal to threshold, or it has to be less than or equal to threshold? Is it for all u comma v or for any u comma v? So how do I formulate the condition? That's the question here. What is the answer? E of u comma v has to be less than or equal to threshold or greater than or equal to threshold. What among these two, if you would like to pick, which one will you pick?
Greater than threshold.
Okay, greater than threshold. Okay, but for which u comma v? For which u comma v? That means for which shift do you want the threshold to be greater?
UV belongs to -1, 1.
Okay, see, -1, 1 is a fine, but I am asking, is it for particular u comma v? Say if it is, say, what I would say is, should I pose this optimization as, say, E of u comma v, summation over u comma v has to be maximum. Is this required? Is this the better optimization? Or E of u comma v, okay, maximum of u comma v, okay, has to be greater than threshold. Is this an optimization problem we would like to pose? Or should we would like to pose, okay, minimum of u comma v, E of u comma v, okay, greater than threshold? Or should I like to pose all u comma v greater than or equal to threshold for all u comma v? Well, how should I pose the optimization problem? See, optimization problem doesn't mean that you just give this, okay, and you should have a single expression. You can't write for all u comma v and then you differentiate with each u equate to 0. That's not the way, okay, in which we do. So we should have a better formulation here. So among, say, these 4 options, which one do you suggest?
First one.
First one, okay, very good. For all u comma v, it has to be greater than threshold. Now, first one is equivalent to what among 2, 3, and 4? First one is obviously true because we have been discussing on that. Okay, so first one is equal to what? Which among 2, 3, and 4?
4.
Only 4. Okay, why 4?
Because if minimum is greater than, every point is greater than.
Yeah, very good. So in case if minimum itself is greater, okay, so it means that it's anyway, minimum itself is 0. If it is greater than a threshold, if it happens, then it is anyway a corner point. If minimum is not greater than threshold, it's not a corner point. So all, if you would like to capture, what is the operation that captures all is minimum. Okay. So what we want to do now, if you would like to pose an optimization problem, is minimize what? Minimize E of u comma v with respect to all u comma v. Okay. And that will give you a solution. Okay. For whatever. So that solution that gives you the minimum value of that E of u comma v you see. Okay. And so first this gives you direction in which E of u comma v is minimum in all u comma v. So this gives u star comma v star. From this you can compute actually E of u star comma v star. And that has to be greater than a threshold for corner point. Okay, is this clear? Hope I
Yes,
hope
sir.
it's clear.
Yes,
Yeah.
sir.
So now, how do we perform the minimization operation? E of u comma v I write here, and that is double summation over xy belongs to neighborhood of xy. Okay, xy can take all the values in the neighborhood of xy. Further, what can happen is, see, as somebody has mentioned before or whatever, so we can give more importance to the central pixel than the other pixels in terms of its information. So we can also multiply this with respect to a weighing function wx comma y such that wx comma y will have maximum value at the center. Okay, and then the minimum value at the like it can go down in the surroundings. So this weight can be like a Gaussian. Okay, so if I considering neighborhood is 5 cross 5 neighborhood, then this w of x comma y will be 5 cross 5 Gaussian. What it gives is, it just gives different weight for different pixels in the neighborhood while computing this difference. So this whole together is what the patch computation. Okay, summation with the summation and multiplication with the w. W is 2 dimension. Okay, so please note that in 1 dimension w is like this. W of x if we see is like this. Okay, so it's a Gaussian in x, but w of x comma y, you can consider it as w in x. Okay, transpose of w in y, if I write it as a vector. Okay, w in x transpose of wy will give me matrix. Okay, 2D matrix, and it's a 2D Gaussian. Okay, so 2D Gaussian I can't sketch better. Okay, so I assume that you can understand here. Okay, it's like this. The contours of equal values will be like this, and peak at the middle. Okay, that's 2D Gaussian. Okay, so that can also be added in the optimization procedure to make a like give more importance to the central pixel, and the optimization also better. So now the whole overall optimization function is w of x comma y and I of x comma y minus, of course you can interchange. Okay, x plus u comma y plus v you can write first or whatever. Okay, it doesn't matter. Not a square. Now the question is, how do I minimize? So my optimization function is minimize it for all u comma v. Okay, minimize for all u comma v, and find out first u star comma v star. Okay, or directly you can find out minimum like e of u star comma v star is like this. Okay, and you can directly, you can also find out e of u star comma v star. Okay, that's what is the optimization. Now, any suggestions on how do we solve it? Let's give the idea and then let's move on. How do I proceed? One very good idea is required. See, one way is differentiate and then equate to 0 and so on. Okay, but they don't want to do that. The reason being, they want to see, Harris in fact wanted to see, can we write this in some sense? Okay, in a compact form, okay, without explicitly differentiating, can I find out E of U star comma V star directly? Okay, I want to find the minimum value and I want to find the minimum U V implicitly and want to use it to find E of U star comma V star explicitly. Okay, can I do that? So what he has done is he wanted to first simplify this and see. Okay, if I want to simplify this cost function itself one more step, any suggestion on how do I do that? One way of solving this kind of cost functions is, see, this can be first we want to simplify this in this part, okay, which is key part. So I of x, say up to, you can simplify to some extent by using some Taylor series expansions, okay? Because what usually is important, it is not very important to have the very accurate solution, but it is important to have a simplified and reasonably close solution. So if I expand this by Taylor series, how does it will be? How can any of you help me in expanding this in Taylor series around x comma y? I want to expand I of x plus u comma y plus v around x comma y in Taylor series expansion. So just like you have actually so how in one dimension, what do you write? I of x comma y, I of x. What do you write in one dimension? Like if you have a I of x plus u, and if you would like to expand in Taylor series, how do you write? I of x naught, that is x here, plus what? What is the Taylor series expansion for I of x plus u? Where you can consider it as delta x. Okay, you know that x naught plus delta x and so on, right? So how do you expand? I of x plus u into dou I by dou x. Okay, right? And so on, plus what? Oh, u square into dou square by dou x square into ix. Of course, there will be some here. What? 2 factorial? What? What is the constant term? And so on. This you can check. Is it 2 factorial?
Divided by 2.
Divided by factorial 2.
What is that?
Divide by 2 factorial.
Right, divide by 2 factorial, correct. Okay, and then here divide 1 by 3 factorial into and so on. You can write, these are all referred to as higher order terms. Okay, and this is the first order term. This is referred to as first order term, where the derivative is of first order, as you can see. So usually when we expand in Taylor series, is good enough to write up to first order term, which captures a lot of information, reasonably good information in many cases. Especially if we assume that the things are smooth, okay, it captures good information. And u is small. Okay, so now if I want to write in 2 dimensions, how do I write? U into dou I dou x plus v into dou I, what should I write here? Dou y plus higher order terms. Okay, so now you can see that whatever we have here is essentially the main Taylor series expansion. This I can neglect. Okay, so now if we bring this in this expression, how does it simplify? Can one of you quickly tell? So I of x comma y and I of x comma y get cancelled. And what else is remaining now? U into ix. I write this as ix because dou I by dou x is ix plus v into iy. Okay, you see a nice or simplified expression for E of u comma v. This I want to minimize for all u comma v. Is this clear?
Yes, sir.
Yeah. You can, those who wish to pursue a little bit, you can pursue to see if we can write this in a simplified manner. Okay, in terms of a matrix M and then in terms of UVs like this. Okay, and that matrix M we can see the properties of matrix M to identify E of U star comma V star data. Okay. So now what we have seen is, we have seen that through Taylor series expansion and taking the first order terms, we can simplify this E of U comma V in this way, right? So now the next, what is the important aspect that Harris has pursued is, rather than explicitly finding derivative, of course, you can find the derivative equal to 0 and so on and do, but without explicitly finding, if we write somehow in this way and then use the properties of matrix, okay, to identify the region where the variance or the variation of this U comma V is minimum among all possible values of U comma V, then that itself is greater than threshold, then we are done. The idea is like this. So as I mentioned, so E of U comma V, so we have simplified before as double summation xy wxy into U ix. Ix is dou I by dou x. Okay, dou where x is actually, I is with two variables. Okay, x comma y. V into iy. Okay, derivative in x direction, derivative in y direction, whole square. Now the thought or the idea from him is that, see, I need to anyway, for all U comma V, I had to differentiate equal to 0, find U star V comma V star and substitute here. That's one procedure. Without even doing without explicitly doing all that, can we do a better way? The answer by him is yes. What the idea is, can I write this whole thing in some sense that, see, U comma V I would like to take out, and I would like to write a matrix here. Okay, let this be 2 cross 2 matrix with M as being the matrix, and this is U comma V. Then how does it look like? It looks like as if, okay, if there is a U comma V is spreading over all directions. If I see in U comma V, so in all directions, if we see U comma V is taking, then among all the possibilities of U comma V, this matrix M in some sense captures an error, okay, or the variance, okay, of this intensity profiles from I of x comma y to I of x plus U comma I of x U comma I x plus U comma y plus V. So M captures variation of intensity from I of x comma y to I of x plus U comma y plus V. Okay, considering all of them. So this is in sense way it captures the variation, means that it is similar to, quite similar to a covariance matrix. In U comma V. Okay, a covariance matrix in U comma V. That means if we have data distribution like this, that means if I have just a set of samples like this. Okay, so if I see the samples are distributed like this in some 2 dimension. Okay, each sample is having these, say I have taken 100 samples and they are distributed like this. Then what I say is, if I see the spread of the samples, that is what is captured by covariance matrix. Okay, so the spread of the samples is high in one of the direction. Spread of the samples is low in other direction here, if you see. Okay, so spread of the samples is maximum in which direction? In this 45 degrees versus in this, say, assume that this is 225 degrees. Okay, so among these 2 directions are here, let's put 135 degrees. This 45 degrees versus 135 degrees. In which direction the spread is maximum of the samples here, and in which direction the spread is minimum? Spread is maximum in and minimum in what? In 45 degrees and minimum in 135 degrees. So if I capture the minimum and maximum directions of the spread, okay, or if I capture the minimum direction of spread, I am done, right? So I know the lowest variance in which direction the variance is minimum. Correct? So the idea is that, so if we consider it is similar to covariance matrix, if I identify the lowest variance direction, directly identify from M lowest variance direction. That is what essentially U star comma V star. Okay, and that gives us directly E of U star comma V star. Is this clear? Now the question is, how do I identify the lowest variance? If I give you some data like this, it is similar to having variation in different directions of U and V for different shifts of U and V. If I give you some direction like this, data like this, how do I identify the data in which the spread is minimum or maximum? Any answer to this? Anybody knows how to identify this? If I give you a matrix M, which is covariance matrix in 2 dimensions, samples are in 2 dimensions, I want to identify the spread where the maximum spread is there, minimum spread is there. Any idea on how do we do this? We can do this by eigen decomposition. Okay, if we write this in terms of eigenvalues and eigenvectors, assume that E1, E2 are the eigenvector matrix. Okay, and this is a phi lambda phi transpose. This is how the eigen decomposition for M happens. And then this lambda 1, lambda 2, okay, essentially provides the directions of the spread, minimum and maximum directions of the spread. In fact, it essentially provides the lambda, whichever lambda I corresponding to the highest lambda I will indicate the maximum direction of spread. If I decompose like this, maximum lambda I corresponds to highest direction of spread, variance. And hence what? Lambda, other lambda, okay, if lambda 1 corresponds to highest maximum direction, lambda 2, other lambda, other than lambda I, where corresponds to minimum direction. Okay, lambda I here are the minimum lambda I, otherwise we can directly take minimum lambda I gives minimum direction, minimum variance direction. Okay, so simply you just see the eigenvalues and then you will be able to find out for which U comma V direction the spread is minimum. Is this idea clear? E of U comma V, if you are writing, I want to separate E of U comma V now. How do I separate is a question. So I will take this again, this one. So how can I write this better? How can I write? I anyway want to separate U of U comma V. Can I write like this or not? Yes? Now, how do I write? How do I write this? This, if I consider somehow as some value including vectors, how can I write is into this transpose. Can I write like this or not? Same thing.
Yes, sir.
Now, if I bring this thing here, how do I write? This is just a mathematical simplification. You see how elegant he has come up with this. So once we discuss the whole method, you will see that this avoids many things. And it is the fastest method for almost one of the best method and fastest method for corner detection. Okay, so U comma V here, and this gives me Ix square Is this clear? Just a simplification. Now I will bring in whole thing and put it here. And what I do is this u comma v, since it's like it is doesn't depend upon x comma y, I will bring this out. Okay, and whichever depends upon x comma y, I will write at one place. Hope you people are understanding. Okay, if you are not able to understand, this is a good time to ask. Okay, so I have just rewritten now whole thing, whatever the equation 1, I have rewritten using, okay, with the simplification in 2. You can see this. This whole thing they refer to as matrix M. Okay, and what is this? Nothing but this is a gradient matrix. Okay, with gradients I have formulated this matrix M, except that this multiplying with a Gaussian at each x comma v indicates that I am performing convolution. Okay, so now in a sense, matrix M is nothing but W x comma y or a W filter. Okay, convolution with, okay, ix square, I will write explicitly here, ix square, ix iy, ix or ix iy doesn't matter, iy square. Okay, so this is what is M. Hope this is clear.
Yes, sir.
Yeah, so we will conclude the discussion now with a small concluding remarks in terms of how they find out the minimum values. So of u star comma v star. As we mentioned, the eigen decomposition will help us in that. So where we have seen that in the previous discussion. So even dropping this W convolution with this Ix, you can also drop convolution with W. You can directly take the gradient matrix also. This is Ix into Iy. Please note that. Gradient in X, gradient in Y. Okay, this is the matrix. So this we can write as M11, M12, okay, M21 or M12 itself. Okay, both are same. M22 at each pixel x comma y. Okay, so now I can perform eigen decomposition here. M can equivalently be written as phi, some matrix, into lambda 1, lambda 0, 0, lambda 2. Since this is a two-dimensional matrix, finding lambda 1, lambda 2 is not difficult. Okay, and once I find lambda 1, lambda 2, I can easily write like this. And this lambda 1, okay, the whichever lambda is smaller, that will give me the direction of small variance. But if I would like to take in general rule, I want to formulate now a rule based on lambda 1 and lambda 2. Tell me, how should I formulate the rule? To have actually E of u comma v minimum for all u comma v. The same problem now I would like to translate to in terms of lambda 1 and lambda 2. How should I translate? Both lambda 1, lambda 2 has to be less than threshold, or lambda 1, okay, or lambda 2 is less than threshold, or lambda 1 plus lambda 2 is less than threshold, or how should I formulate the how should I calculate the same thing, okay, based on lambda 1 and lambda 2? The optimization problem from E of u comma v now need to be translated to lambda 1, lambda 2. That's what is the idea. So how do we do that?
Minimum of lambda 1 and lambda.
Yeah, very good. Minimum of lambda 1 comma lambda 2 has to be less than threshold. Okay, for interest point. Or for minimizing u comma v for all u comma v. Minimizing E of u comma v for all u comma v. Now the question is, this is how actually some of the operators work. Just pick out the lambda 1, lambda 2 for this matrix and see whichever, if it is the minimum of this, if itself it's less than threshold, you consider it as a corner point. But Harris has gone one step ahead and he formulated a cost measure such that you no need even to compute lambda 1 and lambda 2 also. So I would like to have something which without computing lambda 1 and lambda 2, but the minimum lambda 1 and lambda 2 has to be greater than a threshold. Has to be greater than a threshold. Okay. So how he has made is, say lambda 1, lambda 2. See, if I would like to consider product or addition, which is better? When both minimum has to be greater, product is greater or summation is greater? If minimum has to be greater, will the product gives more information on that or summation gives more information on that?
Product.
Say product gives, because if you consider this as 0.1 and this as 100, okay, 100 into 0.1 is 10 only. But whereas add if you do 101, okay, 100.1. Okay, so the addition doesn't really capture the minimum importance of the minimum value, whereas the product captures. So what he has measured, his measure is, okay, so he has formulated based on the product of eigenvalues and the sum of eigenvalues, a measure. The advantage of formulating this is no need to find eigenvalues now. The reason being, I know the matrix M anyway with me. I can find the determinant of matrix M minus k times trace of matrix M and use that simply to find out the measure R. And if R is greater than threshold, it's a corner point. Okay, this is how the Harris has proposed an elegant approach. Okay, for finding corner points, avoiding all the operations of finding the eigenvalues here and capturing for all u comma v, irrespective of the discrete dimensions. Okay, like Moravec has done for explicitly calculating. So at each pixel, what we need to do is simply formulate a matrix with, say, at each pixel now you simply formulate a matrix with ix, find out ix, iy. Okay, simplify matrix M with ix square, iy square, or ix, iy. Okay, iy, ix, both are same, iy square. Formulate a matrix M and then use this decomposition in terms of, no need to decompose, just find determinant and then trace and find out R. And based on that, if it is greater than threshold, declare it as a corner point. So this is one of the best and fastest methods for finding corner points or interest points. Thank you then.